Hello everyone. Welcome to our seventh session of our 3D Thursday webinar series. I am thrilled to have you all with us today, and as we are exploring the world of additive manufacturing. As you may know, additive manufacturing and 3D printing is revolutionizing various industries and different verticals. Our topic for today is mastering copper alloys, revolutionizing additive manufacturing with CuCrZr, the copper chromium zirconium. So we will explore how additive manufacturing is evolving and how alloys like coppers are at the forefront of this transformation. With exceptional conductivity, strength, and durability, copper enables breakthrough innovation across various industries. In this webinar, our expert will discuss the benefits of copper in 3D printing, its key applications, the strategies to maximize its potential for advanced manufacturing. So we encourage an interactive session today. So please feel free to ask your questions. A dedicated Q&A session will be there in place at the end of the presentation. But you can submit your questions anytime throughout the session in the chat. To ensure everyone's question is answered, we may group similar questions together. We'll address as many questions as possible within the time frame. So don't hesitate to share your thoughts. So lastly, please note that this webinar is being recorded. By participating, you consent to the recording being shared for educational purposes. I'm excited to introduce our speaker for today's session, Mr. Suhaib Abdurahman, Manager and Head R&D Quality at Wipro 3D. He spearheads research, quality, and certification efforts with over 13 years of experience in the aerospace manufacturing industry. He specializes in superalloy manufacturing, including additive manufacturing, heat treatment, material characterization, failure analysis, and process troubleshooting. His expertise extends to process audits, quality control, and industry certifications such as NADCAP and AS9100. Notably, he was a key member of Wipro 3D team that achieved the milestone of becoming Asia's first NADCAP approved AM service provider. So let's welcome Mr. Suhaib as he takes through today's presentation. Over to you, Suhaib.
Thank you so much, Manish, for a detailed introduction for the session. Today, I'll be discussing you with the recent developments and the advancement that has happened over the years on copper alloys, especially in the additive manufacturing. So when I was going through the discussion points and what I want to deliver, I wanted to think of where to start with. And I came to know that, maybe we should start with 100 years back. The copper was there. Copper was in predominant in the electrical industry, or is it even more relevant? Is it even more deeply rooted with human beings? So that this gave me the answer that 7,000 years back, when the humankind came out of the Stone Age, they emerged into the Bronze Age. The key reason or key technology that was existing was copper. And the copper helped the technology, the advancement in the technology. Copper helped the man develop new artilleries, new weapons, new devices, wheels. So almost every household, everything at that particular point of time was having the copper. So it was the gold of that era. Then coming the Bronze Age, where the mason or the manufacturer might have accidentally come across some element of tin into the copper, and slowly that evolved into the Bronze Age. So from the Stone Age to Bronze Age, the transformation was through copper, and the copper transformation dates back to 5000 BC. That around 7,000 years back, this was the first metal that human was in contact with. So I'm deriving this statement is inspired by Reed Hastings, and his statement was Stone Age, Bronze Age, Iron Age. we defined entire epics of humanity by the material technology they used. So at present, we are sitting in the digital age, but is it enough? So we are currently discussing, or the future is here, is what the one of the tagline of the event was. So we are discussing about digital copper now, that is additive manufacturing of copper alloys. So in this, I want to explain about how the Wipro 3D came across the CuCrZr or copper alloys, and what is our general approach, and the challenges that are having on 400-watt 3D printing. Also, I want to give you these takeaways where key properties and characteristics can be discussed, and where the applications and adoption would be smooth for this particular alloy. So at Wipro 3D, there are various alloys that we continuously develop, evolve, and develop the parameter for printing, and even sometimes optimize the parameter, optimize the properties, the heat treatments, the advanced post-processing methods. So we develop a lot of the materials and the combination of strength, ductility, and hardness and microstructure. So at present, we are having a various different alloy bases, including iron-based alloys, nickel-based alloys, titanium alloys, and aluminum, copper, and some additional custom alloys that we have developed. So in this, the recent development that has been highlighted here are Inconel 939 and CuCrZr that we are going to discuss today. So when it comes to a problem that some of the designers or some of the our end user, our clients come across, is that they want to adopt additive manufacturing for a certain particular properties, certain strength, certain operating environment, but there are no solution for additive manufacturing. So especially when it comes to maybe high temperature or maybe high corrosion resistance, so there might be no existing solution. So that's the moment then manufacturers or service providers or the researchers in additive manufacturing industry come together to have a approach of material development. So here, when it comes to such problem statement, the first look of any designer will be to choose from the existing materials. So you can see here there is a very high hardness, high tooling alloy, that is managing steel, sitting at the top of the graph. And you also see at extreme temperature, like 1000 degrees Celsius, the additive manufacturing alloys already offers various solutions. And in this, earlier the copper or bronze was sitting at the at 300, at the junction of maximum working temperature of 300 degree with 250 MPa strength. And now with advancement of CuCrZr, you can see that CuCrZr can withstand a maximum working temperature of 400 and sometimes above as well, depending upon the cooling and design and other aspects that is given into the part. So here now, the designers need to come across, and the design to additive manufacturing for not just the part, the material has also should also come across, and develop this technology altogether. So yeah, so coming into the material development, there are various aspects of dynamics, transformation, and mechanics involved. So when especially when we are working with laser powder bed fusion, where very minute particle that may be as small as 30 micron, 40 micron minute powder particles are being molten together and developed into layer by layer manufacturing and developed into the parts. So there are various solidification process, rapid solidification process, plasma condition, the precipitation condition, particle dynamics, and fluid dynamics. A lot of science are coming together to develop this part. So there are various consideration that has to be given while developing a new alloy. So these are some consideration where which is critical to judge whether the part is good, or where the chemistry or the material combination is good for the additive manufacturing process, or we may face some challenges, or is it completely non-feasible? So this kind of approach where weldability will help you. Basically, we are actually melting two minute material particles. So it's welding together, and layer by layer also it is a welding process. So weldability gives a good insight on whether the part could be 3D printed. Similarly, the carbon content, some of the machines, some of the each machine differs in a various way in technology. So some of the additive manufacturing machines may have some limitation, some may have been developed into, accommodate some certain chemistry. So here carbon plays a very important role on controlling how the cooling, especially in the steel, where plain carbon steel like C45 or alloy steels like 4340, where carbon content plays a very important role, and it interferes with the cooling process. Similarly, difference in liquidus and solidus temperature of the alloying elements, or solid solution strengthening elements in the alloy. Similarly, as in nickel alloys, percentage of gamma forming elements plays a crucial role in judging whether the suitability of additive manufacturing is there or not. Coming to the most critical aspect of CuCr or any copper alloys, thermal conductivity, absorption, and reflectivity plays a key role in judging whether, or the key, it throws a key challenge also in developing the parameter for these particular grades. So the approach is that, it always starts from the existing knowledge, literature survey, and understanding the metallurgy of the material, the chemical reactions that may occur. If it required any chemical optimization required, any alloying element has to be modified, or some of the alloying element has to be increased. All these aspects come into the picture. Now, when it comes to the chemistry optimization, if there is also another angle that, the powder manufacturing also has to be feasible, not just the additive manufacturing, the powder manufacturing also has to be possible, and it also has to qualify. So we work in tandem with the powder suppliers, the material the powder development teams, and develop these particular standards together. Then comes the powder quality aspects, where, flowability, or the morphology of the powder, or the porosity inside the powder plays a very critical role in the final quality of the product. So then there is a critical analysis that is happening on, or that we conduct on, the powder porosity, density, the contaminations of oxygen, nitrogen, hydrogen, etc. Then there is an approach of parameter development, where various DOIs will be considered due to the confidentiality or the intellectual property of the reason. I'll not be able to explain how exactly the parameters are developed, or how exactly the parameter that we use it for this particular grade. But I'll be definitely able to explain about what are the outcomes of the product, what are the quality that we achieved. And further to the parameter development, once we achieve a very good solid structure with all the surface parameters, power parameters, and all aspects, then we take it for mechanical property study and metallography. These together in tandem, the studies will be conducted, the precipitation, how the precipitation is happening, what is the strength that has gone up, what are the comparison in terms of the existing alloys, in terms of conventional as cast parts, in terms of the fatigue properties, whether it is comparable with forged component or cast component or extruded component. All this analysis and characterization happens in these last stages. Sometimes we come across that, okay, this particular alloy with this standard heat treatment, it may not be working out. So we also develop a lot of heat treatment methods internally to develop, to improve, and to optimize the properties that the end user demand. So coming to the crust of the topic, CuCrZr. Why it is so important? Why it is most sought after now? This excellent mechanical properties. It is in tandem with the thermal conductivity and the stability. Also electrical conductivity, these set of properties that coming together, it is a very rare combination, and it is widely getting accepted in aerospace industries, in space, in most of the manufacturing, in industrial heat exchangers, uh, in some of the marine piping solutions. So there are a lot of high demand that is gearing up. And when the ease of printing or manufacturing of CuCr ZR is, it becomes easy, and it becomes very feasible for the additive manufacturing, then we have the opportunity to have the design of freedom of higher level, that many complex shapes, many complex structures of heat exchangers with very high surface area, or very complex internal channels. All this can be achieved with additive manufacturing. So that's one key advantage that is coming with this alloy. So what are the key alloying elements in CuCrZr? As the name suggests, it has approximately 98 to 99 percentage copper, and chromium about 1 percentage, and 0.2 percentage of zirconium. So these are the key alloying elements. Even though very minute alloying elements, it adds a lot of improvement without affecting its the pure copper's thermal conductivity or electrical conductivity aspects. So what is the role of chromium in the material? So chromium is added to improve the hardness, strength, and wear resistance, especially at higher temperatures such as 300, 400 degrees Celsius. This also improves the creep resistance where high stress condition over high temperature over extended period of time. And this makes it ideal for many application in aerospace and resistance welding, internal channels, cooling channels, and electrical contacts. Also, the enhanced high temperature strength of chromium is contributing to the main strength of the alloy at higher temperature and extreme conditions, or even in the corrosive conditions. Similarly, another alloying element is zirconium. So zirconium is added to improve the alloy's resistance to recrystallization. So recrystallization is one of the aspect what limits the alloy to perform over certain temperature. So recrystallization, when it is extended or when it is resisted, it has better stability at higher temperature. Also, uh, the uh, the strengthening effect of zirconium, it does not interfere with the electrical conductivity or thermal conductivity, which is the key feature of CuCrZr. And the microstructure refining is another good aspect what zirconium offers to the alloy, that by forming the fine precipitates, it also improves the mechanical properties as well as the strength mechanical properties as well as the refinement of the grain size or grain structures. So in addition to this, it also exhibits better resistance than pure copper in terms of corrosion. So especially this is picking up due to this particular property, it is picking up a lot of demand in marine and aerospace industries. Some of the key application that we can discuss today is in aerospace, the rocket engine nozzles, where it is performing at very high temperature, or so the combustion chambers or combustion engines, where it has multiple internal channels. So the user or the end user can take these kind of components into the consideration, and some of the components are currently running with some of the copper surface treatments, and probably the core is made of stainless steel SS316 or something, and then copper coating. But currently with this alloy, with the freedom of manufacturing in additive manufacturing, we are able to develop, and many success stories are there where the end user is developing fine full CuCrZr or copper based alloy as a full material. Now, when it comes to this section, you can see on the right side bottom of the screen, you can see a lot of internal channels that is used for cooling purpose. So when the conductivity is high and when the surface area is higher in as achieved in additive manufacturing, the the extent of heat transfer is too high that very fast cooling, and it not just the maximum working temperature of the CuCrZr is 400. The cooling effect, which is so fast, helps it take it even further higher temperatures. So these are some of the aspects that designers have to take in consideration and start more inclination towards the CuCrZr or copper alloys for developing the designs. Another industrial application is heat exchanger, or even in automotive, the similar components where heat exchanging is used. And you can see various internal channels on the picture, or various it's sort of lattice structure. It creates a lot of freedom for the fluid to move around and develop the reduce the cooling, increase the cooling effect, and have a lot of flow inside the channels. Now, coming to furthermore application, resistant welding electrode is one example where the spot welding or induction coils, where efficient heat transfer is used for the industrial application. And even in terms of electrical assemblies, the electrical contacts conductors are used for using the CuCrZr. Also, in fusion reactors, sometimes very high plasma phasing components are also used in can be considered for CuCrZr applications. At Wipro 3D, we had it was actually one challenging aspect that was thrown to for the development of this particular alloy was uh, you know in 1000 watt there are machines and 1000 watt which we can develop, and we can have a good quality output, and there are some good advancement there. But due to the high thermal conductivity and even the less absorption of the energy, it is difficult to melt the CuCrZr or copper alloys with slightly lower laser power. So we have at Wipro 3D, we have both 1 kilowatt laser power as well as 400-watt laser power. But we wanted the flexibility of this particular alloy to be used in this low laser power machine as well. So we took it as a challenge, and to develop the part in M280 or M290 machines, which are known for 400-watt laser power. Now, uh, one key challenge in the industry that was prevalent was, or the feedback across the industry was the density issue, where while developing 400-watt, the average density that may achieve is 97% to 98%, which may be detrimental, especially in aerospace application, because aerospace application may have fatigue or high temperature creep applications where the high stress or high load is on the cyclic load is applied on the part, and some of these porosities that may have like 1% to 2% porosities if it is the collective density is around 97-98%. This density act as stress concentrators. It develops into, so it starts having the striation effect, and once the striation effect is started, it acts as the crack initiation sites. And once the failure is happened, once if someone observed that, it will have a crack initiation point at this sort of minor this sort of porosities, which is if it is 1% to 2%, you will see a lot of this microstructure that is shown. A lot of porosities could be observed. So we took this alloy, and we knew that there are a lot of scope for improvement, and a lot of scope for addressing this particular challenge. And we took this parameter. There are around 200 parameters in a 3D printing machine that that can be worked with. So a lot of deliberation, lot of discussion, lot of consulting with various industry experts. We after 3 to 4 builds, we were able to successfully develop this alloy with 99.5% minimum density of the part. So as you can see in the microstructure, the density, the porosity, even though I mentioned 99.5%, here the porosity is only 0.3%. So various sections, various cross sections were analyzed, and various heat treatment cycles were done, and we achieved this sort of even additional heat treatment cycles were employed to improve the mechanical properties as well. Now, coming to the electrical conductivity, and the international anneal copper standards, it's around 100% for the copper, annealed copper, while we were able to achieve, or this particular CuCrZr alloy is able to achieve approximately 80 to 65% of ISES. This range is mainly due to various heat treatment that is playing in as a role of increasing or decreasing the electrical conductivity, because the whenever if the requirement is for particular mechanical properties where you have to have a high load applying on the part, sometimes the application is not intending for the conductivity aspect. Similarly for thermal conductivity as well. So the key aspect, when if it is in the front play, is mechanical properties. There are certain tailor-made heat treatments for having a good mechanical properties and slightly lesser ISCS. Even though it is 65 to 80%, it surpasses most of the other alloys like nickel, aluminum, titanium, and other grades. So just in comparison with silver and copper, this may come in the third in that zone where 80% ISCS is achieved. So if electrical conductivity is the focus, there is a separate heat treatment to achieve 80% ISCS, and if the strength is in focus, there is a separate heat treatment to achieve. But irrespective of if I take HT1, HT2, or HT3, it doesn't fall below 65%. So that's a key achievement. And when it comes to the UTS, the ultimate tensile strength in heat treatment or after heat treated condition, the end user required around 300 MPa minimum, and we were able to achieve 440 MPa, which is exceeding the expectation, and 390 MPa yield strength, which is 0.2% proof strength, we were able to achieve against a requirement of 200 MPa. Now, if so we also conducted a lot of trials on heat treatment where various soak times, various soaking temperature, and various cooling methods were employed. And this particular alloy is so beautiful that it responds so good to the heat treatment, and you can actually develop the heat treatment cycle and you can develop a lot of material combination in UTS combination or UTS to electrical conductivity combination with various heat treatment cycles. So this provides an opportunity for all researchers that may be joined here also to explore this particular aspect where optimizing the heat treatment using the soak time and the set point, set temperature, heating rate, cooling rate, and just changing by 10 minutes, 20 minutes, 30 minutes, there are very good response that is coming from this material. Now, some of the success stories across the globe that I just wanted to bring to your attention is that AMCM developed a 3D printed combustion chamber. You can just see this. So beautifully they have developed, and it is also, various testing has been completed. And this particular data is in more depth. It is available in their channel, and you can see how intricate the structure is. And similarly, with a US company launcher, AMCM developed a different combustion engine in CuCrZr. And as you can see, there are a lot of ports, a lot of internal channels, and even though it might not be visible to you, there are a lot of internal channels in this particular and a lot of various shaped internal channels in this particular design. You can see in the right one where some hint of the internal channels. And this was another key achievement for AMCM that they developed and they even use it for the launch programs. So the launcher is a US company that is extensively involved with the space launch programs. Similarly, the copper aerospace rocket engine was also developed at AMCM. This is sourced at Fabalu, and you can see, a lot of intricate shapes, a lot of complex structures, and this is one typical example of, how a designer can take the freedom of additive manufacturing and design this while the copper also gives a lot of freedom in terms of the flowability, in terms of the fluid, the temperature transfer of the fluid or the internal channels that is going through the part. Now, another success story, what I just want to bring across is that GH induction introduced the coil 3D printing. So for the induction heating system, they have developed it requires a uh, lot of heat generation in the induction coils, and they have developed even uh, the company has even started a new service called serve inductors because they found out that this is a very good market, is very good. This technology has very good advancement. So here I just want to conclude this session and I'll give the session for any further questions.
Thank you, Suhaib, for your valuable insights on copper and its application, how you have come up with the development parameters. So now we are open for the Q&A session, and I have picked up the questions for you. So, so the first question is, what is the optimal laser parameter, such as power, scan speed, hatch space, for achieving high density copper parts in LPVF?
Yeah, so there are certain aspects, some parameters that you can also some of the research papers are available where this kind of parameters are there, and to develop or to achieve the best quality, one may have to experiment a lot of trials, a lot of attempts, a lot of characterization, a lot of testing, and a lot of investment is put into it. So with a lot of effort, Wipro has developed this, and we can discuss on a separate platform wherever, if you want to discuss about certain characteristics that is achieved. But the lesser scan speed, power, and all those kind of aspects are sort of intellectual properties to Wipro, and we will not be able to share on a platform like this. We can discuss separately if you have a advanced requirement or a proposal for collective or joint collaboration on our research and development. Thank you.
So the next second question is, what are the key difference between conventionally manufactured and additive manufactured copper in terms of property and performance?
So in terms of property and performance, it is actually very similar to the alloy. But in conventional manufacturing, there are a lot of castings, a lot of process. So if you extrude, it gives you a certain property. It is much inferior to the if you cast it, or it is much inferior to even additive manufacturing properties. But if you have a very high deformation, say on the forging or cold working or hot working, where there is a lot of grain refinement happening and there is a lot of deformation and work hardening. So all these kind of aspects coming into picture, then there are superior properties also achieved in conventional manufacturing. So it is depending upon the application. It is also depending upon the load condition, the temperature, what the end user is required for, or what is the end service conditions that are being called for. So to brief it, yes, it is comparable to the conventional manufacturing very much, and sometimes it is superior to some of the conventionally manufactured alloys, and sometimes it is slightly below the conventionally manufactured alloys.
Okay. So another question is, what are the challenges associated with powder recycling and reuse in copper?
So when it comes to copper, copper is like I was showing a slide where various alloys like iron or nickel alloys and aluminum alloys are being manufactured. So when the copper is introduced, copper has minor elements of it can create a lot of corrosion. It can act as a the the contamination in the material, the solid material. So any traces that is used or that is being intertingled with the other grades, it creates a big problem. So extensive care to be taken in that aspect in powder handling. And while reuse, we have not come across the property deterioration yet. Even various researchers were showing that there are even improvements over the reuse, and we are continually tracking this reuse performance of copper. Thank you.
So there's one more question with the thermal conductivity. What is the thermal conductivity, and what are the kinds of heat treatment cycles that is recommended for optimal strength?
Yeah. So the heat treatment cycle for thermal conductivity is usually slightly higher than the temperature or the soaking time, that is soaking time and temperature that is required for the strength oriented heat treatment. So various literature that is publicly available will show you like approximately 550 degrees Celsius, which is you can even refer to the EOS data sheets where it explains 550 degrees Celsius, and 3 hours soaking will give you very good optimized thermal conductivity and electrical conductivity. But the point is that there are even further improvements possible in this alloy. That is the point that I was discussing earlier also. So when we took out the trials, there were various different temperature, not just 550 temperature, where the material was actually performing better. So the researchers may come together, they develop these particular alloys and release it to the release as a paper, or even it helps the industry to have less investment on the research and development and more onto the process side. And here, if I want to answer the specific question, the primary answer or primary start point you can have is 550 degrees Celsius, 3 hour. And for strength oriented properties, you can consider 490 degrees Celsius, 1 hour. But further to that, there are a lot of scope, and you can take it as a starting point. You can optimize with various soak time, various heating temperature, various cooling rates, and many other approaches.
So the next question is, what relative humidity of copper powder can be considered, and does preheating of copper powder improve its quality before printing?
So relative humidity should be in the printing atmosphere or in the printing chamber or even in the powder storage area. The relative humidity plays a big role, and it is, if the powder could get contaminated with the humidity, it creates even the end part quality as well. So it is very important to restrict the atmospheric relative humidity less than 60%, and it is also recommended to keep above 35%. So this will help for the powder storage as well as the powder handling area as well as the machine area. This ideal temperature is recommended by all the manufacturers.
So we have another question which says, what would be the maximum operating temperature of the copper alloys?
Yeah, so copper alloys have various maximum temperature depending upon its chemistry. So if you take the CuCrZr, the approximate recrystallization temperature comes around 390 to 400 degrees Celsius. So that's the ideal temperature to use it as the case for maximum temperature. But as I was explaining earlier, the help of internal channels, help of cooling system, and the help of the structure, higher surface area. So all these aspects helps the additive manufactured products to take it a notch higher and use it in even higher temperatures. And even though the recrystallization temperature might be crossed, even then the CuCrZr acts in a very good thermally stable conditions.
So another question that comes across is, did you observe any build volume crack issue or solidification cracks during your print process?
So crack issues was not at all faced by us, but we had some issue with the porosity that we were actually foreseeing that. And initial builds, yes, we had issues with porosity, and it was even on the higher range as well. But with lot of deliberation, lot of discussion, lot of experimental analysis, we came across that challenge, and we solved that challenge, and we are now where we are with very good 99.5 to 99.7 percentage of relative density.
So one more question is, does build orientation affect the anisotropy properties of copper, especially in terms of yield strength?
Yeah, so the anisotropy of the additive manufacturing printed alloys are there, and even in case of CuCrZr, it is actually there. It is a fact, and we have seen approximately around 30 to 40 MPa differences in the yield strength or the UTS when it comes to the anisotropy of the.
Another one is, what are the fastest adopting industries for copper in 3D?
So this is one interesting question. Uh, Copper has been widely used, like I was explaining. It is ancient alloy. It has been used in almost all the industries, but the fastest adopting, if you ask, fastest adopting industry was aerospace. Actually, it could be not just because the copper is suitable for the industry. It could be also that aerospace industry has been a pioneer in adopting the additive manufactured products, be it aluminum, ALSI 10mg, be it Inconel 718, be it nickel alloys, nickel-based superalloys. It has been the aerospace industry has been very aggressive on adopting the additive manufactured components. But other industries, especially in Indian scenario, other industries are slowly coming up. There is also a higher demand from the process industries. There is also demand from the heat exchanger manufacturing companies. So it is coming up. Also, marine is also have certain demands that we have come across. So yes, it is actually suitable for all industries, but the way we see it, it is more engaging in the aerospace industry.
So another question that has come across is that you mentioned IACS varied from 65% to 80%.
Yeah.
What is the reason for such large variation?
So this is basically in the heat treatment. So the variation, when I was talking about the conductivity specific heat treatment, the if you achieve so you're basically changing with precipitates, you are basically having the solutionizing aging process. So with these constituents and this with precipitation level, there are certain differences that are achieved in the conductivity domain. So if you are focusing on the higher conductivity level, if you use same heat treatment, if you use same process, a qualified process for additive manufacturing and heat treatment, then there will be a stable. It is not not like same process you will achieve 65 to 80. It is not the case, but based on the heat treatment, even in the conventional, that is the same case. Because if you take in the casting CuCrZr, you will see this difference when it is compared to a forged or hot worked CuCrZr. Similarly, when you achieve a different kind of matrix when you achieve different kind of microstructure, you have this expected as same way. Even mechanical strength, it is in the as printed condition you can get as high as 250 MPa, but in the heat treated condition you will get it as high as 440 MPa, 450 MPa. So same way, when the material's internal matrix and internal constituents, the precipitation level changes, then the properties also changes along with it. So this is nothing about the additive manufacturing. It is more about the post processing and the internal material matrix.
So the next question is, can you elaborate a little bit on the porosity control techniques and when printing specifically copper to maximize the part integrity?
So the porosity, it can originate from the powder. So one key aspect is to have a very good specification for the powder, qualify it, and have a thorough examination of the powder itself. As is the case in any other manufacturing, raw material is the key source of quality, right? Be it chemistry, be it any other morphology, be it the porosity, the raw material is a source of porosity or any other quality issue. So characterizing the raw material, characterizing the powder, which is the raw material here, and uh, doing a very extensive SEM uh, powder checks like Hall flow analysis, apparent density analysis, and tap density analysis, and even some of the microstructure level analysis, along with particle size distribution analysis using X-ray methods, or uh, even some of the analysis. What we do is we even print the small coupons, and as a sample coupons we take it and we observe. So all this qualification of powder is key to this. Secondly, optimizing the parameter as well, as you have rightly asked it. And there are certain aspect that goes into, and some of the aspects are actually intellectual properties of Wipro. So how to optimize this particular porosity is, along with the process parameter, along with the powder control, along with the final part qualification, we can overcome this challenge.
So the next question is from Rohit, who says, how does Wipro 3D support customers in transitioning from prototypes to production using CuCrZr?
Okay, so Wipro 3D has a consulting arm called Advise, and we have various success stories where we helped our customers achieve or productionize their prototypes into multiple qualified components. Some of the instances where we developed a lot of parts for our Indian ecosystem and qualified for airworthiness. So airworthiness or CEMILAC, Center for Military Airworthiness. So airworthiness is something, there are a lot of extensive testing and everything. So there we pitch in with our knowledge of additive manufacturing, the DFAM aspect where design for additive manufacturing is employed, and we help the customer in the complete consulting process from the prototype to productionize by all the by maybe design optimization. Maybe sometimes there is a qualification process that is not established, so establish how to establish the qualification process, qualification protocols, qualification documents, the digital passports. Sometimes even our end customer comes with a reverse engineering aspect where there is an existing part, the supplier is actually not providing the components, or they have shut their doors, or even there is other supply chain issues like the geopolitical situation. So these kind of times when reverse engineering is another solution for all our end clients. So at that time we pitch in with complete reverse engineering strategy from the part material to the part delivery. So even there are some recent cases where we actually we got a particular alloy which is called HRS, heat resistant steel, and we were able to. So this was not at all existing anywhere in the ecosystem of additive manufacturing when we developed that, and we took the part. we reverse engineered its chemistry. We developed the powder itself, and with, of course, with the collaboration of our vast network of suppliers. And the powder was developed, and then we did a lot of trials to develop the parameter for that 3D printing parameters, including the scan speed, laser power, and all the parameters that, and various build, various attempts, and finally, and there were a lot of feedbacks that this is not at all, this is very difficult alloy to be manufactured. And finally, we were able to achieve that, and we were even able to achieve all the end functional requirements as well, and all the critical assembly requirements, assembly testings, leak testing, and even fatigue testing, the creep stress structure testing. All the testings were, even engine level testings were completed. This was very class one critical component, and we were able to deliver to our client. And that has even productionized as a result. So, you know, we would like to engage in this type of particular queries or particular uh, aspects where the customer wants to get productionize certain prototype. We want to engage from the starting itself, from the chemistry side itself to the end point. I hope that answers your question.
So next question is, are there any recommended in situ monitoring techniques for copper to detect defects during the printing process?
Yeah. So it comes with certain machines. It may not come with certain machines of 3D printing, but there are in situ monitoring technique, like EOS has a camera, inbuilt camera inside, which is suitable for melt pool monitoring, where layer by layer you will have an understanding of what's happening in the machine, and each layer, how the solidification, or whether any cracks or any chip off or any sort of defect that is coming into the build can be analyzed with this sort of multiple monitoring techniques. And most of the machine manufacturer are providing these options as an uh, uh, optional function. So it is there, but if you are a 3D printer, then you will have to, if you do not have this one, then you will have to go back to your manufacturer and say, hey, we need this, and this could be possible. And at Wipro 3D, yes, we do have the multiple monitoring system, and we utilize that. Thank you.
So next question is, have you thought about post-processing? What kind of surface treatment can be done for post-processing?
Yeah. So most of the cases we have, because of no surface treatment as such is required because of the kind of application that is being used. But there are various options to improve, and see, copper alloys are very good response for most of the surface improvement, like mechanical polishing aspect itself. So it improves a lot in that way. But sometimes what customer requires is in the as printed condition itself, without any particular surface treatment, coating or anything, because they want to utilize the maximum benefit of copper. And apart from that, we also are venturing into certain new post-processing aspect to improve. There are certain aspect in 3D printing where support structures, removal time. There is a downskin effect if you are familiar with additive manufacturing, and where the surface too high surface roughness may have a problem with the end use. So those kind of cases we have certain methods. We are also trying to improvise many techniques like micro machine polishing, or even abrasive flow machining, and many certain post-processing techniques are there. We are trying to explore, but at present, we have been our end users have been demanding for a as printed surface with certain limited machining.
So the next question is, what future developments can we expect in copper-based alloys and 3D printing materials?
So there are, like I was highlighting earlier in the part of presentation, there are various application even in the marine, even in the process industry is coming up. Even though aerospace has taken a notch up, and they have even developed the aerospace industries many firms have even developed a 3D printed rocket engine combustion chamber with CuCrZr and various other the examples that I was displaying. So in marine and in the process industry, I see a lot of scope and a lot of advancement. Now, when it comes to the 3D printing, there is also a certain aspect that we need to improve is in the on the heat treatment side. There are a lot of options, a lot of opportunity to improve the material strength and properties and conductivity together in the heat treatment, because as the case is evident, there are a lot of changes in the properties happening during the heat treatment. So the target of additive manufacturing process as it is in extrusion should be to achieve a very good high dense, high strength, high density, in particular high dense property, while the functional properties and optimization of those should be achieved in the heat treatment trials. And this gives a good opportunity, and we could even expect a better advancement in terms of strength and properties.
So we'll take two more questions. So one is, we normally see color gradients in the printed parts. So what exactly is that, and why is that?
So color gradients, it you might be seeing it after certain time. So what we have observed is there are no color gradients at time of printing, but during especially it is when I was talking about heat treatment, I should have mentioned this, that inert gas atmosphere of post processing is very important, so especially in the heat treatment. So the inert gas especially like argon atmosphere or even vacuum is recommended for the post heat treatment of the CuCrZr. And CuCrZr is prone to oxidization at high temperature, especially in the nascent surface. So even in the AOS datasheet or any public datasheet, you would probably be observing this. If you are looking at application in the as printed condition, then utilization of inert gas furnace is mandatory or requirement. Especially more than nitrogen, it is better to use argon itself or better vacuum. Now, if it is to be machined, or if throughout the surface has to be machined, then you can actually utilize in the regular electrical furnace itself, given that the whole surface is machined in the post process.
So we'll take one last question that says like, what uh, or how do you control the reflection issues that you face, specifically because copper reflects most of the laser energy and it's highly reflective. So how do you overcome that?
So in case of the machine setup or the machine, say EOS M280 or M290, we have a standard setup, and we have been given a limited, opportunity to, play with the reflectivity. So the material is there, it is reflective, and we have a certain laser. So there angles you can work with, and certain other aspects like post scanning methods you can work with. There are certain advanced methods where we can discuss this bit separately, because it may involve some of the intellectual properties that we have already developed.
All right. So thank you so much, Suhaib. Thank you for your valuable insights and patiently answering all our questions. And it was a very valuable insight into the 3D printing capabilities of copper, its application across various industries. And thanks everybody for joining us today. You can still connect with us over the website or email, where we can help you with further questions. So with this, we would like to conclude. We appreciate your engagement and the thought-provoking questions that you raised during the entire session. Your participation has truly enriched this discussion. So as we wrap up, we are also excited to announce our next webinar, which will take place on April 17th, the third Thursday of April. We'll delve into another fascinating topic that continues to shape the future of technology and manufacturing. So thank you once again for being part of today's session, and we look forward to see you next time as part of our Wipro 3D webinar series, 3D Thursday. See you.
So thank you everyone for listening, and it was a very good participation from all the attendees, which is what even I wanted to achieve, giving a lot of time for the participants to ask questions as well. Thank you so much.